Okay, so in the last video we talked about moment frames, our first lateral force resisting system. And the nice thing about moment frames is that they don't really change the look of the structure very much. In fact, someone without knowledge of structural engineering may not even be able to tell the difference between a gravity frame and a lateral moment frame, other than that the sizes of the columns and beams may be a bit larger, or if they're particularly observant, that the detailing of the connections is slightly different. And we'll get more into the detailing later next week. But for the most part, moment frames are the least obtrusive structural lateral system. And so architects tend to really like moment frames because they don't impede on the elevation of the building. However, not all buildings are suitable for moment frames. In fact, their use is limited primarily to shorter buildings less than 3 stories tall and in low seismic zones. And this is because moment frames are not particularly rigid. And so for anything outside the scope of what I've just listed, we need to add more rigidity to the lateral system. So let's now talk about our next lateral force resisting system, brace frames. Like trusses, brace frames keep all joints in the frame pinned, and we convert the perpendicular force into an axial force with a diagonal member, like this. So when this 2-kip force pulls on this frame to the right, the brace will go into tension. And if we push in the opposite direction, that brace will go into compression. And it's important to note that each brace will be designed for both tension and compression. And that's of course because our lateral loads can come from either direction. Wind doesn't just blow constantly in one direction. So we've already analyzed trusses pretty extensively, and analyzing a brace frame is really no different, except that now we're looking at something vertically instead of horizontally. So just think of brace frames like vertical trusses. So let's now discuss different types of brace frames. This terminology will be important to know when working with structural engineers, who will often throw out these terms without realizing that not everyone in the room may be totally familiar with what they are talking about. So first we have the most basic, a single diagonal. And you'll see this a lot on the East Coast. On the West Coast, however, and in higher seismic zones, there are requirements to have braces in 2 directions within a single bay for certain types of buildings. And so next, we have an X-brace, or a cross brace. Third, we have a chevron brace, which is often a very popular configuration as it allows architects to place openings between the braces for doors or windows, etc. Next we have an inverted chevron, and finally we have a knee brace, which you may see used for supporting wood decks outside your typical suburban house. Knee braces aren't often used for large-scale buildings as they behave more or less like a moment frame. You can see here that a force generated in this brace will have a horizontal component to it, which will put this column into bending. And so really all that we've done here is fix these joints and basically created a moment frame. And we're still relying on the bending strength of the column. Whereas these other braces with full height diagonals are able to take that lateral force directly, axially, down to the supporting elements. Overall, brace frame buildings tend to be more efficient and have a lower embodied carbon than moment frame buildings. This may seem counterintuitive because with a brace frame, we're adding another element, whereas the moment frame was just the beams and columns. However, recall that structural elements are far better at resisting axial forces than bending. And so, with a brace frame, we are able to keep these columns and beams relatively small. And these diagonal pieces as well can typically be relatively small, compared to if this were a moment frame, the amount of increased steel we would have to add to get the stiffness we need for the frame. So brace frame buildings tend to have a lower embodied carbon than moment frame buildings. So brace frames are more efficient than moment frames because they resist lateral forces axially and not through bending. So finally, we have our last lateral force resisting system, which is a shear wall. By far the most rigid lateral force resisting system that we will cover in this course. This is because shear walls have the advantage of having a completely solid wall of material to transport lateral forces directly to the ground through shear. A short 10-foot masonry wall like this with a 2-kip force applied would basically not move at all. So shear walls provide the most lateral resistance by far, but they are not necessarily always the most efficient solution. And that's because, as we just mentioned, they use a lot of material. Also, they take a lot of time to build, which can slow down the project schedule. So it's important to be able to recognize appropriate opportunities for when to use shear walls. The first thing you should ask yourself when considering shear walls for your building is, do I have any fire-rated stair or elevator shafts in my building? These shafts will often be made of relatively thick, solid CMU or concrete walls to achieve the necessary fire rating for the building. Also, the shafts will likely be continuous up the full height of the building. Those continuous solid walls need to be there for architectural purposes already. Making them into structural shear walls only requires a bit of extra reinforcing in the wall, and a more solid connection to the building's diaphragm. And that's it. Just a few extra pieces of steel, and you have a very rigid lateral force resisting system for your building, using materials that would already be there anyway. And so you can't really get any more efficient than that. But the other thing you need to ask yourself before you go changing all your shafts into shear walls is this. Are these shafts centrally or symmetrically placed in my building? If not, that could cause more problems than it's worth, as we saw earlier. So when we talked about seismic irregularities, if we have an elevator shaft in the corner of the building, and we tried to make that into our lateral force resisting system with shear walls, then this building would experience a large amount of twist around those shear walls. And we would end up with a torsional irregularity. And note that even if we were to place some moment frames or brace frames elsewhere along the building to try to balance out the pull to this shear wall element, that may not necessarily help, because shear walls are so much more rigid compared to brace frames and moment frames. And we still would likely end up with this torsional irregularity. And so, if this elevator shaft definitely cannot move from this corner for architectural reasons, the building may actually be better off if we simply leave this elevator shaft as an architectural component and don't try to tie it in to the structural system. So shear walls themselves are very rigid elements, which can either be a good thing or a bad thing for the building depending on their location. Okay, one final calculation here and then we're done for the week. Let's look at how to calculate the base shear and overturning moment of a shear wall. Let's look at how to calculate base shear and overturning moment of a lateral resisting system. And here I've drawn this empty box, which could be interpreted as a shear wall. But really this could be any type of lateral force resisting system, and this calculation would be the same. When we talk about base shear and overturning moment, we're talking about the total force at the base of the structure. And so everything that happens in between is inconsequential for this analysis. All we care about are the base reactions. So actually I drew that red, so I'm going to change these to red as well. So the base shear is very simple. We just add up each of these story shears, and we get 12 kips for the base shear. For the overturning moment, now we need to look at these story shears and their distance from the base of the structure. And so we have 5 kips up at this top level, which is 36 feet from the ground, plus 4 kips times 24 feet, plus 3 kips times 12 feet. And hopefully compared to the math from last week, this is much easier. And so we end up with 312 foot kips for our overturning moment. And with that, we're pretty much done with the math in this course. Congratulations to all who have survived. I really do appreciate your efforts so far. Next week, we will be diving deeper into how we select different types of structural systems given different building types. And we will start discussing the 4 most popular structural materials, which are steel, concrete, wood, and masonry. So with that, good morning, good afternoon, and good night, and best of luck to all of you on the midterm.